Okay, so hope you are all fine and you are liking our modules on Verilog. We have compiled and presented few modules earlier. So if you are new here first time, you are encouraged to go back and refer to those modules. We are also going to give you the description of those links. Now, let us focus with this example right over here, which is Verilog modeling again. And this time we are going to model a basic NOT gate, which is as shown in this figure. So for example, this is a NOT gate. And we know that the logical operation of this truth table is that Y output is not of A. So complement of A. That is how it is carried out. Here is a circuit of a CMOS inverter where you have NMOS and PMOS. This is an NMOS. Here is a PMOS. When you apply logic 0, you have output logic 1. And when you apply logic 1, you have an output logic 0. So this is an actual circuit that you want to implement using Verilog. Okay, so obviously this is a hardware, a very simple hardware using 2 transistor. So the truth table, we know that the truth table would be obviously input is A, output is Y. There are two possible combinations for the input, and accordingly you will have the complementary output. For 0 input, logic high. For logic high input, logic 0 output. How to write the code? So here it is very simple. There are two types of modeling. One is data flow and one is gate level or a structural level. So data flow modeling, as we have seen before, we are just describing in the code the Boolean expression, form of a Boolean expression. We don't write the Boolean equation or expression. Rather, we write a command or a syntax that will just say how the data is being transferred from input to output, and the syntax for that is a statement assign. We have used it in our previous model. So how do you start that? You start with module and then you have to write end module. Always remember, you start with module and end module, and in between I am going to tell you what you do. So after writing the module, tell the name of your circuit, INV, that is an inverter. Then in bracket, define the inputs and outputs. Output is Y, comma, input is A, and then don't forget to put this semicolon. Then say what is your output is Y, semicolon. What is your input? A, semicolon. And once that is done, simply write this expression. We know that the Y is equal to A complement. Okay, that is a Boolean form expression, but in Verilog, you will use this keyword assign, and output variable is Y, input variable is A. Note the parenthesis is not required here, but it doesn't harm if you use it. So just say exclamatory sign that indicates the not operation, and then say A, that is the input. And then end model was already there. So this is example of data flow modeling. Here you can see that this command can also be written as assign Y, and you use this sign instead of exclamatory sign. This sign can also be used in Verilog. Okay, so that's your data flow modeling. What about the gate level or a specific you tell how the hardware is to be implemented? So basically you are saying that use a NOT gate. If you use this, implement this circuit in FPGA, you are telling that I want to instantiate a NOT gate. So gate level modeling is like you are instantiating a particular logic gate, and using those logic gate, you are implementing that logic. So again, you write module, end module, obviously, give a name to the module. I have given I and B, that is inverter. You can use also example or whatever, or not get whatever. And in parentheses, I have defined output and inputs Y comma A. And you can also write A comma Y. So that order is not to be maintained here necessarily. You can use any order. And then you say, don't forget to add semicolon. And then you say output is Y semicolon, input is A semicolon. But now look at the difference right over here and right over here. Instead of using the command assign in gate level modeling of Verilog, you simply write the keyword not, that is the command, and then G1, that is the gate one. Okay, so I'm writing, and then in parenthesis, output must be written first, and then it is followed by an input. You cannot have the reverse way. A cannot come first and Y cannot come later. Okay, so unlike here. Okay, so Y is the output comma A, and then you have like semicolon. Okay, now one thing that is to be noted is you have this hashtag 10 that indicates the delay of the logic gate. So here you have this delay of 10. The unit is not given, so unit has to be specified in the code somewhere. We have done that in our previous module. So let's say 10 nanosecond is the delay. So it means when you are switching at the input from 0 to 1 or vice versa takes place, it will take 10 nanosecond or 10 units of time to reflect those changes at the output from 1 or 0. I say again, it will take 10 nanosecond, that is the inherent propagation delay of a NOT gate or any logic gate for that matter. So when you have a switching at the input, they will be switching at the output, but it will be at the after the 10 unit time units. Okay, so it depends on nanosecond or picosecond. Okay, so that's why you can define this the delay, that is the propagation delay. Then obviously you have the end module. Once you have this code, then you can confirm whether the syntax is right or wrong by just copy pasting or directly writing this code in the Verilog compiler. There are a lot of online compilers available, cloud-based, or you can download and install in your computer and then open that compiler, the Verilog compiler, and then just start writing the code in the compiler itself and then execute. So if the syntax is correct in both of these gates, you will run into zero error. And that's what you want. Okay. And after compiling code, you can check, verify the coding through the simulation by writing a test bench, which is basically another set of code that applies stimulus to your circuit. For example, stimulus to this circuit is logic 0 or 1 as an input, and accordingly you monitor the output. So that is the job of a test bench. Okay, we'll see that how we write that. And then you are done with the simulation. Then next step is the synthesis, which will generate the gate level netlist based on this code, and accordingly your circuit will be then implemented. Okay, so hope you found this model useful. If you did so, share it with others for a wider range, and stay tuned for more engaging content like this. Till then, we wish you a very happy learning.